Hi everyone, welcome back to the Tox Lab. I'm Rebecca.
I'm Rob. This week we're going to be having another look at nitazenes. We first looked at nitazenes a few weeks ago, and this week we're going to be looking at the structure-activity relationship of nitazenes and how different nitazenes vary in their characteristics. Before we get into that, I want to briefly go back over what nitazenes are and why we care about them. Nitazenes are novel opioid drugs. They were first developed in the 1950s by a Swiss pharmaceutical company, and they were looking for alternatives to existing opioid drugs to be used for medical reasons. And they synthesized the compound etanitazene. They tested it, they patented it, and decided that it showed no clinical benefit, and actually it had quite severe adverse effects. It was incredibly potent. It caused quite a lot of respiratory depression. And so at that point, nitazenes were broadly forgotten about. And then in 2019, there were the first reported cases of nitazenes emerging as a drug of misuse. And slowly these started to appear in forensic cases, in post-mortem cases, in drug seizures. And very soon we then had this wave of nitazene analogues, or nitazene variants. Today we often encounter nitazenes mixed in with heroin. We see nitazenes in counterfeit medications and sometimes sold as powders in their own right. And they really have turned the world of toxicology upside down in these last 18 months. So Rebecca, with that in mind, why don't you take us through the paper we're going to be looking at today?
So as Rob mentioned, nitazenes are novel synthetic opioids. So opioids are a class of drug that act on the mut-opioid receptor in the brain, and their main role is to provide analgesia or pain relief. So other drugs in this class are morphine, codeine, fentanyl, things we've kind of all heard of. They also provide sedation, they can provide euphoria, nausea, and in higher doses can cause negative side effects like respiratory depression, which can be fatal.
So the opioid pathway endogenously is part of the body's way of modulating pain. If you hurt your foot, initially your foot will hurt, and after a while that pain will fade away. And it's through opioid receptor mediated pathways does that internal pain relief occur. And opioid drugs, they hijack these endogenous receptors. And medically, they're very useful because they can cause analgesia and reduce people's pain in a medical setting. But if you stimulate these receptors too hard, they can also cause euphoria and, as Rebecca said, ultimately can be fatal.
So nitazenes, or 2-benzyl-benzimidazole opioids, which is an absolute mouthful to say, are a broad structure of synthetic opioids. And you can modify this core structure in different ways, and that will alter how potent and how well they will bind to these mu-opioid receptors, and therefore what sort of effect they're going to have. So this study looked at characterising a set of 15 different nitazenes, some of which had been predicted to emerge, hadn't been seen before, and looked at substitutions in 3 different positions on this core structure that we know have an effect on how potent they are, and then 1 previously uncharacterised position. Basically just wanted to see what happened to how well they bind to the receptor, and therefore how potent they are, as they did this through a variety of in vitro, like cell-based experiments, and then in vivo experiments in mice.
So they took a core structure of a nitazene, they tried lots of different chemical variations at various positions on the molecule. Then they looked to see how well these molecules interacted with the opioid receptor in various ways.
Yeah, exactly.
To think about this, an opioid receptor is a particular shape and it acts a bit like a lock, and drugs that hijack the receptor act a bit like a key. And the question here was, of all of these molecules, which of these is the key that best fits the lock?
So the first experiment they carried out was a radioligand binding assay, and this experiment is designed to see how well these nitazenes bind to the receptor, or in other words, their affinities. So for this, they used a synthetic opioid peptide, also known as Damgo, which was radio-labelled. And basically, this will bind to the mu-opioid receptor, and they wanted to see whether the nitazenes, when they were introduced, outcompeted this radio-labelled peptide for the receptor. So those that have a strong affinity for the receptor will displace this Damgo protein, essentially.
So it's a bit like musical chairs. Your chairs are your receptor. You've got your radio-labelled opioid ligand that's jumping in some of the chairs. Plus, you've got your nitazenes, who are the other players. And if the nitazenes are really potent, they're really good at musical chairs, and they're pushing the other radio-labelled ones out the way. And you measure the radioactivity, more radioactivity, less nitazene activity, effectively, because you've displaced it in the really potent ones.
This showed that the 15 nitazenes they looked at all bound with a nanomolar affinity. One of the nitazenes, 5-methyl-etodesinitazene, had the highest affinity out of the 15, and ethylene nitazene had the lowest affinity.
So all of these nitazene variants bound to the receptor. So they were all active to some degree, some with more affinity than others.
Yeah. 5-methyl-etodesinitazene had a higher affinity than some of the nitazenes that we have studies for, so ethynitazene, isodinitazene, and beta-nitazene, but had a lower affinity compared with metanitazene and the reference compounds they use like fentanyl and morphine. So once they assessed how well these nitazene compounds bound to the receptor, they wanted to see whether they actually activated the receptor, because just because a drug binds doesn't necessarily mean it's going to activate the receptor. So the mu-opioid receptor is a GPCR, so it's a G protein coupled receptor. And when a ligand, in this case nitazene, binds to it, the receptor undergoes a conformational change, can recruit a load of proteins that allow signalling within a cell so that an effect can occur. So basically, for this assay, they utilised a luminescent enzyme called nanoluciferase and split it in half. And one half was attached to the mu-opioid receptor, and the other half was attached to a protein called beta-arrestin, which gets recruited to this receptor when it becomes activated. So once a ligand binds, it's going to activate the receptor. You'll get phosphorylation of the receptor by GPCR kinase, which then allows the recruitment of beta-arrestin. And when you get the two halves of this enzyme within close enough proximity to each other, and you add in a substrate, you then get bioluminescence, which can then be measured.
So the first assay, they were measuring how well these opioids bound to the opioid receptor. But in the second one, it was a question of how well can they activate it, or how strongly can they activate it. So this is done at multiple concentrations, and we can draw a graph.
Yep, you get an S-shaped curve, and you can use that to assess potency, which is the concentration or dose of a drug required to produce 50% of its maximal effect. So essentially how much is needed to achieve an effect. And it also looks at efficacy, which is the maximum effect that can be expected.
So a drug can be potent, i.e. cause an activation at a relatively low concentration. But what we were also seeing is that these drugs also have a very high efficacy. They activate the receptor really, really hard.
Yeah, so ethynitazene, which is the nitazene that's been previously characterised, was the most potent. And ethylene nitazene was the least potent of the 15 nitazenes that they tested. And interestingly, methionitazene and alpha-methyl-etonitazene are the only new nitazenes that they looked at in the study that had a greater potency than fentanyl.
So a lot of these modified nitazenes, although they were activating the opioid receptor and showed some potency, they were not as good at activating it as fentanyl. Yeah.
And interestingly, bar a couple of the modified butanitazene nitazenes that they looked at, isobutanitazene and zecbutanitazene, none of them were more potent or had a higher efficacy than their primary nitazene. So when they've modified ethynitazene, for example, none of those modifications made them more potent. So after their in vitro experiments, they then decided to take 6 different nitazene analogues through in vivo experiments to kind of see how they worked in a mouse model. So they looked at propylnitazene and then 5 of the most potent analogues of ethynitazene, which included ethylenoxynitazene, 5-methyl-etodesinitazene, 1-ethyl-pyridinyl methyl endosalkyl ethynitazene, which is an absolute mouthful.
These are all long words, you're saying.
Alpha-methyl-ethynitazene and ethylene ethynitazene. So they assessed 3 main features. So they looked at locomotor activity, so basically how will the mice move at different doses of these nitazenes. They looked at body temperature through a subcutaneous sensor that they'd implanted into each mouse. And then they looked at hot plate latency, which is basically the time it takes for the mouse to react to a heat stimulus. And any reaction can be flicking their paws, licking their paws, jumping about, things like that.
And thinking about what's going on biologically, it's a marker of analgesia, isn't it? You've effectively interrupted those pain pathways.
All 6 of these nitazenes showed dose-dependent changes in these categories. All of them reached maximum levels of blocking a painful stimulus. The most potent was alpha-methylethanitazene, and the least potent was ethylene-inoxynitazene. And what was quite interesting is, as you increase the dose of these nitazenes, you get quite a linear decrease in body temperature and increase in antinociception. So basically, pain relief.
Pain relief, yeah.
So in terms of locomotor activity, it showed a biphasic response, so kind of a bell-shaped curve. So at lower doses, the mice were travelling around less. Their distance they travelled increased with increasing dose, and then their distance travelled decreased at even higher doses.
So there seemed to be some sort of mid-dose something going on?
Yeah, I think so. So these 15 nitazenes that they've looked at and characterised, at the time of them starting the study, hadn't been seen in the drug market. They were all nitazene analogues that they'd predicted based on what we know about structures and modifications to each of these different groups on the core structure. So, but 4 of these, since the start of the study, have now been seen on the recreational drug market, and this includes 5-methyl-etodesnitazene, ethylenoxynitazene, ethylene ethanitazene, and isobutanitazene.
So they successfully predicted the emergence of some of these nitazenes.
Yeah. It'll be interesting to see if any more of them make an appearance on the recreational drug market, or whether because they're not quite as potent, they might not. Who knows?
So is there anything we can learn about the structure-activity relationships of nitazenes from this data? We know that taking the nitro group off to make the desnitazenes seems to reduce the potency.
Yeah.
And increasing the chain length on some of these seems to decrease the potency.
The chain length's a bit of a funny one, because relatively short chain lengths are more potent than very short or long linear chain lengths, or ones with halogens in them. So there is kind of definitely a sweet spot in terms of the chain length.
So in the wider context of nitazenes then, we've got these big collection of chemicals. They're all slightly different chemically, and they've all got quite different potency characteristics, haven't they? Some of these exceedingly potent, 1,000 times more potent than morphine. Some of them quite a bit less potent than that, although they are still all quite potent, aren't they? We are still talking about compounds more potent than morphine. So I think even the least potent of these nitazenes actually is still quite potent compared to some things. How did the results of the receptor binding and beta-arrestin recruitment compare to the mouse potencies?
They only ended up picking the 6 most potent nitazene analogues from the receptor studies to test on the mouse models. So we don't know if one that didn't perform particularly well in cell-based assays actually might have been more potent on the whole in a mouse model. We just don't have that data, because mice are expensive.
I'm just thinking that when you change a chemical like this, you're doing multiple things, aren't you? You're affecting how well it affects the receptor.
Mm-hmm.
And clearly, if you modify a chemical in certain ways, if you imagine a receptor is a 3D space and your chemical fits into that 3D space, you alter how well it fits into that shape.
Yeah.
But the other thing you're doing is you can affect effectively its bioavailability, how well it can go from injecting it into a mouse into the brain. And so if you were to make a compound much more lipid soluble, it might not fit into the receptor quite as well, but it might still have much greater bioavailability.
Yeah.
Nitazenes, as we know, are quite lipid soluble compounds in general anyway, aren't they? So they are quite bioavailable from what we understand.
And while we have this data for some of these in a mouse model, it'd be interesting to see how they translate to humans and whether they translate like for like, or whether there are subtle differences that affect how bioavailable they are in humans versus in mice.
Completely fair, yeah. So I'm aware of another study, we could put the link in, looking at isotonitazene and N-desethyl isotonitazene, which is a metabolite of isotonitazene, but also has emerged as a drug in its own right. And N-desethyl isotonitazene seems to have much higher receptor activation than isotonitazene, but yet in a mouse model had less effect. And that we think is due to the fact that it is more polar, it's more water soluble and not as fat soluble. But as Rebecca says, actually we don't know how well any rodent data translates to humans. We've got studies in other opioids that give you some ideas of how well rodent data and human data compare, but we simply don't know when it comes to nitazenes.
And on the back of that, we don't really know how sort of potent and active the metabolites of these nitazenes are, and whether in fact they may or may not be more active and more potent than parent drugs. There's still very limited data on even the ones that have been around since 2019 on the sort of metabolites that are produced, and then those haven't necessarily all been characterised either.
That's a really good point. The in vitro experiments tell you one thing about one chemical, don't they? Whereas the mice model, there's actually 100 variables in play, really.
Yeah.
You've got the metabolism aspect, you've got the bioavailability and so on. And yeah, I think that definitely, given the sort of anomaly, if you like, with regards to N-desethyl isotonitazene, there probably is still quite a lot to learn about the metabolism and how relevant that could be in toxicity, for sure.
And as well, with some of these metabolites appearing as drugs in their own right, as we've seen with N-desethyl protonitazene, N-desethyl isotonitazene, how much that complicates our interpretation when we are looking at these cases and trying to understand whether they are there purely as a metabolite or they are there as a drug in their own right, contributing in different ways. It's such a raw area of toxicology that we're all struggling so much to try and make sense of it all.
I do have to give a big shout out to the team that did this work. Nitazenes are an area of interest of mine. They've taken over our life for the last 18 months or so, and without this sort of raw work looking at the activity data, we wouldn't know where to start when it comes to looking at what this stuff means. So I guess the question then, the big question, so all of these nitazenes studied, although some of them have now emerged in drug markets, all of them were less potent than some of the previous nitazenes that we've seen.
Yeah.
In other words, this study didn't identify a brand new nitazene that was suddenly more potent than etonitazene or N-desethyl isotonitazene or anything like that.
Yep.
So what's next? Will nitazenes continue to evolve but continue to get less potent? Have we reached peak nitazene?
That's a good question. I don't think anyone really knows. I hope they don't get any more potent, because as they currently stand, they're terrifyingly dangerous and are doing a lot of damage.
I was thinking about this morning in terms of the discovery of carfentanil. So I don't know if you've come across carfentanil, but it's a fentanyl analogue that's maybe 100 times more potent than fentanyl. And it's used in... Oh, we always end up talking about elephants on this podcast. It's used to sedate elephants via a dart gun. 5 milligrams will bring down a 5-ton elephant.
Oh,
so,
wow.
you can imagine just how potent this is. And you just imagine these scientists in the 70s thinking they've hit peak fentanyl, and suddenly someone discovers carfentanil. And so I guess that's the question, is there a carfentanil version of nitazene just around the corner that we haven't yet figured out?
I really, really hope not, because I cannot begin to imagine the impact that's going to have if that ever gets into the drug supply. We've seen nitazenes in so many different things as contaminants in heroin, but then contaminants in benzodiazepines, which is really frightening. I cannot think of anything worse than a more potent nitazene than what we've already seen.
Okay, so in summary, a number of novel nitazenes have been synthesised, tested in various ways, and although they're all potent opioids. All of the chemical modifications so far seems to be decreasing potency. These compounds have now been characterized, so we can test for them, which is really helpful. But crucially, we haven't stumbled across something exceptionally much more potent, and possibly, therefore, we are past peak nitazene in terms of potency.
Although while we might not see ones that are more potent than what's currently out there, we could still keep seeing so many different ones that still make it really analytically challenging.
Okay, so I think we're going to wrap it up there. I hope you've enjoyed listening this week. Do give us a like and follow on social media.
You can find us on Instagram at _tox_lab. It'd be really great to hear from you. Feel free to comment on any of our posts and any of our episodes. You can send us a message. You can also comment on Spotify now, which is really cool. I just want to give a big shout out to all of you guys. We've recently hit 200 plays across all our episodes, so thank you so much for listening. We're really pleased that you're all enjoying our content. If you've got any episode suggestions or anything you'd like us to cover in future episodes, let us know and we'll try our best to include it. Hope you all have an amazing week and we'll see you next time. Bye.